Okay, so some of these might require a little bit of thought and thinking about like the unit circle or something like that. But let's take a look at this one right here. So just a decimal approximation for this. This is about 1.4 divided by 2. So this should be about 0.7. Is that what you got? Okay, this is about 1.86 or something. And then if you divide by 2, so what did you put? 0.8, 0.9? 0.8? Okay, we'll put 0.8 there. Either one. I mean, if you wanted to be a little bit more accurate, we could put 0.86 or something like that. Okay, what about radical 3 divided by 3? 0.58? Okay. Okay, 0.6 if we were to round to the nearest tenth. And then radical 3? About 1.7. Okay. So then what we're going to do is we're going to take each one of these numbers and we're going to find the reciprocal, okay? So if I take 0.5 and I do the reciprocal of that, or take 1/2 and find the reciprocal, I flip that over, okay, and I end up with a 2. What happens if I take 0.7 and I do the reciprocal of 0.7, or 1 divided by 0.7, or take that and do 2 divided by radical 2? What do I end up with? About 1.4? Okay. And what happens if I do 2 divided by radical 3? 1.2. And what about the reciprocal of radical 3 over 3? 1.7. And this guy right here? Reciprocal? 0.56. Okay, so about 0.6, somewhere in that neighborhood. Is that right? Okay. All right, so let's figure out what the secant of pi fourths is. So we've actually done this before, but these are not the values right off of the unit circle, but they're pretty close. Secant is related to which trig function? The cosine. So this would be the same as asking what's 1 over the cosine of pi fourths. Okay, and the cosine of pi fourths is one that we're really familiar with. So this would be 1 over radical 2 over 2. So if I were to flip that over, it's 2 over radical 2, right? It's that reciprocal. So isn't it this value right here? It's about 1.4. Okay, and the secant of 5 pi 6. So let's see, that would be 1 over the cosine of 5 pi 6. And what's the cosine of 5 pi 6? Think about that unit circle. It'd be 1 over negative radical 3 over 2, right? So if I were to flip that over, it's going to be the reciprocal of this one right here. It's going to be, whoops, negative 1.7. Is that what we got there? Did I erase the right thing? Or put 1.2. Okay. So negative 1.2. Should we check this? Okay. Grab your calculator if we want to check and make sure. So what we're trying to find here is the secant of 5 pi 6. So I'm going to turn the calculator on, clear this stuff off, make sure I'm in the right mode. I'm in radian mode. Okay, and now I don't have a secant button on my calculator, do I? So if I want it to calculate a secant, what do? I do 1 over cosine. So I'm going to do 1 divided by the cosine of, and I just type in 5 pi 6. So we're going to do 5 pi 6 negative 1.15, so if we rounded, we'd get negative 1.2. Everybody okay with that? So it's the right value, okay? Cosecant of pi 6. Cosecant is related to the sine. It's the reciprocal of the sine, so this would be 1 over the sine of pi 6. And what's the sine of pi 6? Remember, that's that short leg on a 30, 60, 90, so that would be 1/2, wouldn't it? So this is 1 over 1/2, so the answer to this is 2. First nice number we've come across, pretty much. Okay. Cosecant of 2 pi thirds. So that's going to be 1 over the sine of 2 pi thirds. Let's see, so we'd be in quadrant 2. The y-coordinate would be that long leg of the 30, 60, 90. So that's going to be radical 3 over 2. So flip that over. Positive 1.2, isn't it? It's that reciprocal that we found right there. Okay, and then tangents and cotangents. So let's do tangent of pi 6. So if we wanted to think about what that looks like, this is 1/2, this is radical 3 over 2, and it's the y-coordinate over the x-coordinate, the opposite side over the adjacent side. So we take 1/2 and put it over radical 3 over 2. Flip that over, we end up with 1 over radical 3. And 1 over radical 3 is approximately, isn't that this one right here? If we rationalize, so this is going to be 0.6 roughly. And then the cotangent, how are the cotangent, now notice this is the same angle, it's both pi 6. How is the cotangent of pi 6 related to the tangent of pi 6? They're reciprocals. So what's the reciprocal of this guy right here? It's radical 3, which is 1.7. Roughly. Okay. Any questions? Okay. Now, this next one, we'd have to change the mode on our calculator. Not a common angle, 89 degrees. What's the tangent of 89 degrees? What'd you get? 57.2. Anybody confirm that? Okay, if you changed into degree mode, you'd get 57.2. Now that is a gigantic number. That is a very big number. Can somebody tell us why that number is so dang big? I mean, everything else we've been dealing with fairly small numbers. Why is the tangent of 89 degrees such a big number? What two sides are involved in the tangent ratio? Okay, so opposite and adjacent, or the y-coordinate over the x-coordinate. So if I were to draw a picture of roughly what 89 degrees looks like, okay, 89 degrees is a very, very steep angle. And if we were to draw a reference triangle for this, we drop a line straight down to the x-axis, right? So we're talking about the comparison between the opposite side or the y-coordinate and the adjacent side or the x-coordinate. Okay? It's a ratio between the two of those. And if you've got a really large angle, you've got a gigantic opposite side and a very small adjacent side. So we're taking a big side, dividing it by a really small side, and doesn't that produce a big number? Okay, so that's why the tangent of 89 is so big. Do me a favor, type into your calculator the tangent of 89.9. What'd you get? 572, so we add another 9/10 of a degree. Just make it a little bit steeper, but I mean, it was already really steep to begin with. 89.9 is almost straight up and down. We made the opposite side a lot taller and the adjacent side a lot smaller, so we get a much larger number. Does that make sense? Okay, so when we're dealing with these ratios and reciprocals and comparing big numbers and small numbers, we get some pretty interesting results. Okay, so now I want to write down the reciprocal of just some fractions. Okay, or some whole numbers here. What's the reciprocal of 1/5? Now we're to the easy ones, right? Reciprocal of 1/5 is 5. What's the reciprocal of 1/10? 10. The reciprocal of 1/1000th? 1,000. Okay. What's the reciprocal of 20? 1/20th. And the reciprocal of 100? 1/100th. Okay. So here's what reciprocals do, and this is why we're really interested in this particular section, because secant and cosecant, those are reciprocals of the trig functions sine and cosine. Okay? So if we know something about the values of sine and cosine, we can figure out something about the values of secant and cosecant. Okay? Because they're reciprocals, reciprocals take big numbers like this, and they make them really small numbers. So they make big numbers small, and they make small numbers big. So the smallest number we could get in absolute value, if you wanted to speak of it that way, would be 0. What's the reciprocal of 0? Would be 1 over 0, right? And 1 over 0 is undefined. That's one of our domain issues. So undefined. Okay? There is no reciprocal for 0. Okay? So what is the reciprocal of a small positive number? Now think about this before you answer, because I typically get part of the right answer, but not the whole right answer. If you take the reciprocal of a positive, what type of number do you get? Positive or negative? Still positive, right? So it's still positive, but the reciprocal of a small number is a big number. So if I said this way, if I say, what is the reciprocal of a small positive number? You're going to say it's a big positive number, right? And what's the reciprocal of a small negative number? A big negative number. Okay? All right, now, that took us 10 or 12 minutes to go through that little exercise about talking about reciprocals, reminding ourselves of how we find values of sine and cosine and secant and cosecant and tangent and cotangent and stuff like that. Okay? But these ideas now, if you think about these for a second, are any of those very difficult? I mean, even this question right here, like why is the tangent of 89 degrees such a big number? Okay, that makes sense now, doesn't it? Okay, so here's what we're going to do. And again, this is good practice. Everything in trigonometry somehow comes back to sines and cosines. Okay, we graphed this yesterday, but notice the interval I want you to graph the sine function on. I want you to graph it from negative pi halves to 5 pi halves. So you can start just on the normal interval from 0 to 2 pi. So 2 pi is right here. So it starts at 0, goes up here, down to here, down to here, and then back to there. But this would be 5 pi halves right here. So it's going to be back up to 1. And at negative pi halves, it's going to be down at negative 1. So we're graphing more than one cycle. We're graphing a little bit extra. So it's going to look something like this. And again, like I've mentioned several times, try and make it a nice looking curve. It comes up there and flattens off for just a bit. So 0, 0, pi halves, comma 1. And again, we mentioned yesterday, you ought to be able to do this in about a minute or less, hopefully. Everybody good? Should be about that quick. I mean, I have a little bit more practice, but once you know what it is, I mean, we should all be about as quick. Okay, so that's what it should look like. Should put arrows on the end here, just recognizing that this could go on forever in both directions. So what's the domain of the sine function again? What type of angles can you plug into it? Are there any restrictions on it? Nope, anything you want. So from negative infinity to positive infinity, anything you want there. What's the range? Okay, 1 to negative 1, or we usually list the smallest one first, so negative 1 to 1. And what type of brackets, round or square? They're going to be square, because it does actually go down and hit a value of negative 1, and it comes up here and hits a value of positive 1. It does that over and over and over and over again. Okay? Any questions there? Okay, I'm going to make this a little bit smaller, and I'm going to slide this up here so we can see that on the page here. So we're going to graph the cosecant function. Okay. Now, of all the trig function, I would say cosecant and cotangent. For some reason, they're my least favorite, but that's what we're going to start with here. Okay. So we're going to graph that on the exact same interval, and we're going to take advantage of the fact that the cosecant of an angle is 1 over the sine of an angle. Okay, so I actually have the values that I need to find the reciprocals for right here. Okay, so I'm going to graph a couple of extra points here. Okay, I'm going to graph this point right here. That point right there is pi 6 comma, isn't it 1/2? Okay. At this point right here, it's pi 4ths comma radical 2 over 2. And the last common angle in quadrant 1 would be pi 3rds comma, isn't it radical 3 over 2? So it starts off at 0, 1/2, radical 2 over 2, radical 3 over 2, and then 1, right? Okay, aren't those the values that we memorized from quadrant 1 on the unit circle? Okay, everybody good with that? Okay. If I were to do this point right here and say that was negative pi 6 comma something, what would it be? If this is pi 6 comma 1/2, wouldn't this be negative pi 6 comma negative 1/2, right? Okay. All right. And wouldn't I have some values over here that are exactly the same? Kind of corresponding or symmetric values. Everybody good with that? Okay, so we're going to take these values right here and we're going to come down here and we're going to graph what the cosecant would look like. So the easiest value on this little curve right here to find the reciprocal of is right here. Okay, what's the reciprocal of 1? It's 1. Reciprocal of 1 is 1. So I'm going to come down here. And the reciprocal of 1 would be 1. Okay, so what I'm saying there is that the cosecant of pi halves should be 1 over the sine of pi halves. And the sine of pi halves is 1, so the cosecant of pi halves is 1. Does that make sense? Should we double check that on the calculator? I mean, we could do that really quickly if I just type in 1 divided by sine, and then I'm still in radian mode, so I'd do pi divided by 2. Tells me it's 1, right? Okay, let's take this value right here, pi 6. What's the reciprocal of this one? It'd be 2, right? So if I come straight down here and I'm at pi 6, the value on cosecant should be 2. So this would be pi halves comma 1. This right here would be pi 6 comma 2. Now again, let's do the same thing. Let's check this on the calculator. So I'm just going to recall that last command and I'm going to type in pi 6. And if our reasoning is correct here, it should tell us that the answer is 2, and it does. Okay? So are we doing okay so far? Okay. Let's follow this one over here. The one that would correspond to this one would be, how many pi 6? So which one over here, which angle over here has the exact same value, 1/2 for a y-coordinate? What would it be? 5 pi 6. 5 pi 6. Think about the unit circle. If we go up pi 6 here and up pi 6 here, okay, this is pi 6, this is 5 pi 6 correspondingly over there, okay? So at 5 pi 6, follow that straight down. What's the reciprocal of this y value? Should be 2. So this isn't a little kind of curve that just oscillates up and down like that does. Okay, it's kind of going upward. Okay, and just for the heck of it, just to double check and see, I'm going to recall that, and I'm going to type in a 5. I'll insert a 5 there, and we'll double check. It does tell us that it's 2. Okay, so our reasoning is perfectly sound here. Now, here's where it gets a little bit interesting. What about this value right here? So I've taken pi 6 and I've transferred the reciprocal value here. It was 2. Taken 5 pi 6, transferred the reciprocal value here. Pi halves was the easiest one. Its reciprocal is just 1. What's the reciprocal of 0? Undefined, we don't get an answer, right? Okay, so what I'm going to do down here is I'm going to make an asymptote. In fact, anytime the sine has a value of 0, what would the value of the cosecant of that angle be? It would be undefined. So if you try and find the reciprocal of 0, you're going to get something that's undefined. Okay? Same thing here. Okay, these are all small positive numbers. Everybody with me? Need you to watch up here. Every one of these values on the sine curve is a small positive number. What's the reciprocal of a small positive number? A big positive number. And in fact, the smaller you get, the bigger the reciprocal is, right? So if there was a value right here that was, say the y value right there was 1/100th, what would its reciprocal be? 100. So the closer we get to 0, the larger the reciprocal is, right? So what that means is, here's what the curve looks like, okay? It's going to be huge positive numbers here. They're going to get smaller and smaller and smaller. The smallest one is going to be +1, okay? And then the closer we get to this asymptote, the steeper it gets. Now, is that a parabola? Is there any way that could be a parabola? No. Okay. Parabolas continue going up and out. Okay. This can only go over so far before it hits that asymptote. Okay, and only so far in this direction. So it kind of looks like a parabola, but it's not. It's not anywhere close. It's more like a U shape. Okay, so it comes down here, flattens off for a second, and then goes back up. Okay, now are there any questions about that? Because if you get that, then we can speed up the rest of this. Any questions? Okay, so I'm going to label one more point. This one was 5π6, 2. Now, everybody watch. What do these values right here have to do with these values right here? They are exactly the same, but they're negative. Okay? Exact same y values as we get here on this little loop for the sine function, but over here they're negative. So this value right here is -1, and what's the reciprocal of -1? -1. So we're going to come down here and we're going to put a value right here of -1. So this is 3π12, -1. Now let's pick the easy ones to do, the ones that have nice reciprocals. Okay, π6, back up π6 here, you get 5π6. If you went forward π6, you'd get 7π6, -1/2. So if I follow this straight down here, what's the reciprocal of -1/2? -2. Same thing over here, and this would be, let's see, if I were to back up π6 from 2π, that's going to be 11π6, and that's going to have a value of -2 also. So it's going to look like this. Okay, maybe not exactly like that, but you get the idea. This is 7π6, -2, and this is 11π6, -2. Okay, now, what happens here? What if I do the reciprocal of each one of these? If I get a loop going upward or a branch going upward, okay, and a loop going downward or a branch going downward, what do I get right here? Yeah, you get a 1/2, okay? Or, I mean, it really continues, right? This pattern just goes on and on and on, okay? And what do I get over here? I get kind of that branch going downward. So the cosecant function looks like this. It has an asymptote at 0. It has an asymptote at π, an asymptote at 2π, And because these are small positive numbers, this has a branch that goes upward. Because these are small negative numbers, this has a branch that goes downward. And the closer you get to one of those vertical asymptotes, the bigger the numbers. So on this side, they get really big in the positive direction. On this side, they get really big in the negative direction, because take this number right here. Say that was negative 1/100th. The reciprocal would be negative 100. It would be way down there, okay? So it gets really, really steep as it approaches those vertical asymptotes. Any questions? And it just goes over and over and over and over again. Branch upward, branch downward, branch upward, branch downward, okay? What's the period? How long does it take this to repeat the entire cycle? Because an entire cycle is a branch upward, then a branch downward, then a branch upward, then a branch downward. It is, somebody said it, it's 2 pi. It's just like it is for the sine function. If the sine function has a period of 2 pi, then the cosecant function is going to have a period of 2 pi. What's the domain for the cosecant function? You can plug in anything you want except for, do I get a value right here? Nope. Value right here? Nope. Okay. So not at 0, not at pi, not at 2 pi, not at 3 pi, not at negative pi over here. So we could say it's going to be all reals, negative infinity to infinity, as long as x is not equal to, and this is how we'd write these asymptotes down, or how we'd write down the what the domain is not. It's anything except for k times pi, and k can be any integer. So pick any positive or negative whole number, including 0, put it in for k, and that will be a number that we can't plug in. It's also an asymptote. That would be the equation for the asymptotes. Pick any positive or negative whole number. Pick a 2, plug it in there. Is that where an asymptote is? Okay. Pick a negative 3. Would there be an asymptote at negative 3 pi? There would be. Okay. What about the range? The range is a little bit strange on this one. The range would be the y values that we get out. Okay, so kind of squish the graph onto the y-axis. Do we get any answers way down here? We do. We get a bunch. Where do they stop? They stop at negative 1. So this is going to be negative infinity all the way to negative 1. Round or square around the negative 1? Square. And then we don't get any answers in between negative 1 and positive 1. And they start up again at positive 1 and they go to positive infinity. Okay? Now, here are the 6 key points that you'd want to know. And really, I'd be okay if you can do the asymptotes and maybe 1 point on each branch. The 6 key points would be right here. Okay, they're the ones that have the nicest reciprocals. All the other reciprocals, they're pretty ugly, pretty darn ugly. Okay, so those would be the points that you'd want to be familiar with. Any questions? Okay, let's go ahead and flip the page over then. And we're going to do the same thing for cosine and secant. So I'm going to graph the cosine function from negative pi halves to 5 pi halves. So this one starts here, goes down like this. And I'm hoping we can make this a lot quicker. We're getting pretty good at this by now, right? Okay, domain is all real numbers, so from negative infinity to infinity. I should make that look right. And the range is from -1 to 1, including those endpoints. So we'll use square brackets. Okay, here's how we're going to graph the reciprocal of cosine, or the secant function. We're going to find the reciprocal of every one of these values right here. Okay, but we're going to do it in a smart way. If I try and find the reciprocal of 0, what's the reciprocal of 0 again? Undefined. So just like on the sine function, wherever the cosine hits 0, we're going to come down here and we're going to make a what? A vertical asymptote. So there's going to be a vertical asymptote here, a vertical asymptote here, here, and here. Those are all vertical asymptotes. Then we're going to be smart about the way we find reciprocals. Okay, everybody look up here. Take a look at all of these cosine values. Okay? This loop of small positive numbers, when you find the reciprocal of small positive numbers, what do you get? You get big positive numbers. So this is going to create a loop that goes upward, like this. Now, this one's pretty easy to find the reciprocal of. The reciprocal of 1 is 1, so it goes like this. It has exactly the same shape as the secant, or the cosecant function. It just occurs in a different place. Okay, in this next one, this is a little loop of small negative numbers. What's the reciprocal of small negative numbers? Big negative numbers. So this is a loop going downward, loop going upward, and so forth. Okay, now let's see if we can label these key points here. This one would be 0, 1. I'm going to have a point right here and a point right here. Now, the cosine doesn't hit 1/2 until we get to pi thirds. So this point right here is pi thirds, 2. If this is pi thirds, 2, what would this one over here be? Negative pi thirds, 2. Okay, and I want to point something out here. So if you've written those things down, everybody watch, please. From this center point of this branch, this branch is centered right here at 0, 1. I go pi thirds this way and pi thirds that way. Everybody okay with that? If I come back up here, let's take a good look at this one. If I was at at pi halves, and I went pi thirds this way, wouldn't that put me at pi 6? Isn't pi halves minus pi thirds, isn't that pi 6? And if I take pi halves and I add pi thirds, isn't that 5 pi 6? So these shapes are exactly the same, okay? And if this one right here is at pi, reciprocal of -1 would be -1. And if I go pi thirds over here, whoops, I should put that in a better place. If I go pi thirds over here, this is going to be 5 pi thirds, -2. And this is going to be, let's see, if I subtract pi thirds from pi, that's going to give me 2 pi thirds, -2. And then it just goes on and repeats and repeats and repeats. Okay? So there are the 6 key points that we'd want to be aware of. Again, if you can get the shape right, get the asymptotes correct, and maybe graph this lower point here and this upper point right here, this minimum on this branch that goes upward and this maximum on this branch that goes downward, that probably would be okay. What's the period? Period is 2 pi, just like it is for the cosine function. The domain is all reals except for wherever there are asymptotes. So let's think about how we'd write down these asymptotes. And this might require some thought, and we'll write this down here as well. This is what I think is the best way to write down these asymptotes, because they repeat every so often. Now, you'll notice that on this one, how far was it in between every set of asymptotes on the cosecant function? It was pi, right? Isn't that the same thing here? Okay. So the way I normally like to write these down is I'd write down, so this is x equals pi halves. This is negative pi halves. And this is x equals 3 pi halves. Pick one of these to start with, so give it a starting place. So I'm going to say x equals pi halves, and then you say how often it repeats. How far is it in between every set of asymptotes? That's going to be pi, and just put a k in front of it. So this is going to be all the x's except for pi halves plus k pi. If I put a 0 here, remember k can be any integer. If I put a 0 here, I get pi halves. Is pi halves one of my asymptotes? It is. If I put a 1 here, what's 1 pi plus pi halves? 3 pi halves. Isn't that where this one is? If I put a negative 1 here, pi halves minus pi, isn't that negative pi halves where that one is? Okay. Now let me just show you that on this one as well. One way that we could write this down would be x equals, the first one is at 0, and then how often do they repeat? Every pi units. So instead of writing x equals k pi, I could have said 0 plus k pi, and that tells me where the first one is. It's a little bit redundant, a little bit too much on that problem, but that idea does work. If you have something that repeats like this, write down a starting place and then just k times how often it repeats. Okay, that's going to come up again, so I would keep track of that. What about the range? What type of y values do we get out? It's the same shape as cosecant, it's just been moved a little bit. Okay, so it's the same thing. The range is going to be from negative infinity to negative 1. Skip a little bit and then start up at 1 and go to positive infinity. Okay, any questions? Okay, grab your calculator then, and we're just going to double check a couple things. Okay, that's in radians, so make sure your calculator's in radian mode. We want the secant of 1.56. So this is going to be 1 divided by cosine of 1.56. So you got 92 something? Okay. 1.56 is just a little bit less than pi divided by 2. 1.57 is pi halves. So let's look at this right here. On the secant graph on pi halves, remember we've got an asymptote right there. So this is 1.57 right there. That's where the asymptote is. If I type in 1.56 for secant, I get 92. I get a gigantic value. It's way up on this branch, way up there. Does that make sense? Okay. All right. Any questions there? Okay. These are pretty funky graphs. Okay. They're pretty wild. They're probably the most complicated thing that we see in a trigonometry class as far as graphing goes. Okay. But once you get those ideas, and once you have the basic idea of what those parent graphs of secant and cosecant look like, well, then we can go through and we can transform them using those same things that we did with sine and cosine. You can take the same parent graph and you can move them around. Sounds like a ton of fun, doesn't it? Okay. Take some complicated shape and then do something more complicated with it. Okay, so let's start off with something really easy. Okay, if that were, say this was a cosine graph, and it had a 2 in front of it, what does that do to the cosine graph? Vertically stretches it, right? Okay, makes the points bigger than they used to be, taller than they used to be, further from the x-axis than they used to be. So it's a vertical stretch. That's all this does to the secant function. So I've got a graph of the secant function sitting right here. And the only thing that this does to that graph is it makes the points taller. So instead of being at 0, 1, where would it be? 0, 2. So it's going to be right here. Now, does it change where the asymptotes are? Doesn't change anything horizontally. All it does is make the points taller. So I'm still going to have an asymptote here, 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 and here. I'm still going to have a branch that goes up. And next I'm going to have a branch that goes down. Where's it going to start here? Where's the highest point on that one going to be? It's going to be at -2, right? So it's going to look like this, and like that, and so forth. Okay? Now, oh, this should say graph 1 cycle. Sorry about the typo there. Okay? I would be fairly happy if you could come up with where the asymptotes are and label this point right here and this point right here. So this point right here is at 0, 2. This point right here is at pi comma -2. And where's this asymptote? -pi halves, 3 pi halves. Okay? We've graphed one cycle of 2 times the secant of x. Okay. We took that graph that we just did up above, this one right here, and we vertically stretched it. We made the points, the y-coordinates, we made all the y-coordinates taller. We didn't change anything else. Okay? Any questions there? Okay. Let's take a look at this one right here. I'm going to change colors for this one. Just pretend that this was y equals the sine of 2x. What would the 2 do to the graph of sine? Change the period. It's going to speed it up. It's going to cycle faster, right? So that's what's going to happen to this one. Okay? It's going to be the same type of shape. So I'm actually going to graph this one right here. It's going to graph that faster. So the new period is going to be 2 pi divided by 2. So the period is going to be pi, right? So it's going to do this. That's one cycle of the sine function, right? And this is 0, and this is pi. And this would be pi halves. So if I were to graph this guy here, it's going to be the reciprocal of these. It's going to go like this, and it's going to go like this. Make that fat so it looks like they're the same. So where this one has a 0, this one has a vertical asymptote, vertical asymptote, vertical asymptote. And let's label that point right there and that point right there. Where would this point be? Pi fourths, comma 1. And this would be 3 pi fourths, comma -1. And could we write down an equation for the asymptotes? Remember, write down where they start. They'd start at 0. And how far is it in between each asymptote? Pi halves. So plus k pi halves. Or we could just write x equals k pi halves. That's where the asymptotes are. Those are the numbers that aren't in the range, or aren't in the domain. Any questions there? Okay, take a good look at this. Okay, notice that this has a one branch going up between 0 and pi halves, and one branch going down between pi halves and pi. Let's come back up here to the original one, the parent graph. If I made this cycle faster, wouldn't it make this branch going upward in half the time? So wouldn't it make it in between 0 and pi halves? And wouldn't it slide this one, so instead of in between pi and 2 pi, it would be between pi halves and pi. Wouldn't that horizontally shrink it, horizontally compress it? Does it make sense? Okay. All right. If you look on the website, I updated the homework. So I have homework on the website for these sections. We've only graphed secant and cosecant. Next time we're going to graph tangent and cotangent. So here's what I would do. Go to the website. Grab that. And if you go right here under chapter 4, let that load. Down at the bottom, it's got the homework. And I've got a calendar on there also. So let's take a quick look at this. So here's the homework. Okay, so I filled that in. And then I'm thinking we can finish 4.6 on Monday. It'll take us a couple days to cover 4.7. We'll review next Thursday, and then we'll have a relatively short exam. It probably won't be full length, but it'll check to see whether or not you can graph sine, cosine, secant, cosecant, tangent, cotangent, and 4.7 we're going to do the inverse trig functions. That's all will be on that. Just 3 sections on that test. Okay? All right. Have a great weekend. Okay? Enjoy that, and then I'll see you on Monday.